So first of all, thank you very much for the invitation. It's a pleasure to be here. So I will talk about some applications of Toposes of Measure-Theoretic sheaves. So, and I will start with a very elementary example. We all know from calculus's theorem, so in continuous function, from a compact Hausdorff space into the real numbers is bounded and attains both a maximum and a minimum. So historically, this theorem was first proved for the compact real interval, and the proof relies on two main ingredients. So the first ingredient is a Bolzano-Weierstrass theorem, so every bounded sequence has a converging subsequence. And the second ingredient is a Dedekind completeness of the real numbers. So this means that any bounded subset of the real numbers, regardless of the cardinality, either it is countable or uncountable, has a supremum and an infimum. Okay, so we would like to randomize this statement. So one way to randomize this statement is as follows. So first of all, we pick a probability space. And then we look at the compact valued correspondence. So this is a set valued map from X into the power set of the real numbers, which takes compact subsets of the real numbers as values for each X. And we consider a function, a bivariate function, from X times R to the real numbers, such that for each fixed X, this function is continuous in Y. Now we would like to know under which assumptions is the following optimal value function measurable. So here, obviously, for any fixed X, we can just apply the extreme value theorem from the previous slide and obtain there a minimum, because Kx is compact. But the question is, when is this function measurable? So in general, this function is not measurable. We need some additional assumptions on the compact valued correspondence and on this bivariate function f. So the Kuratowski-Ryle-Nardzewski measurable selection theorem gives a sufficient condition for the existence of measurable selectors or measurable functions with values in this set-valued map Kx. So a measurable selector is just a measurable function such that for each x, fx lies in this set-valued map Kx. And this is the Efros measurability condition, which states that the set of all x for which Kx intersected with a given open set is non-empty should be measurable. In this case, we can guarantee that the set-valued map has measurable selectors. So this is one sufficient condition we need. And the second, additionally, we also need that the function f is what is called a Kara-Theodori integrand. That means that additionally to being continuous in y for any fixed x, it must be also measurable in x for any given y. In this case, we can prove that this optimal value function is measurable. Okay, so this is related to the subfield of descriptive set theory, which is known as measurable selection theory. And the basic strategy of measurable selection theory is that, first of all, it involves a pointwise formalization. So we work here with points, as you said, as you saw in the previous slide. We have a set-valued map, which takes for each point in the underlying probability space some compact subspace in the real line. And we apply in each fiber a classical theorem pointwise. Right? So for example, in the previous slide, we applied in each fiber the Bolzano-Weierstrass theorem for each fixed x. But then we are looking for sufficient conditions which guarantee that we have measurable selections. And those conditions usually involve some form of separability. One could, for example, wonder what happens if you replace the real numbers with some other topological space. And the best measurable selection theory can offer is that we can work with Polish spaces, so complete and separable metric spaces or metrizable spaces. And we need at least closed valued correspondences, measurable, like satisfying the F-ROS measurability. So one can wonder if one can relax these assumptions if you replace pointwise by pointwise almost everywhere with respect to the given function. So we request that all the relations are satisfied almost surely with respect to the probability measure, but this won't remove the restrictions of this theory, such as separability or closed valued correspondences. So there are a number of applications of measurable selection theory, like in stochastic programming, optimal control theory, calculus of variations, game theory, mathematical economics. I will also come to some other applications later on in the talk in the realm of ergodic theory and vector functional analysis. So let's try a different approach now. So now we want to try a direct point-free approach, and formalize the same randomization problem slightly differently. So we denote by L0 the set of all measurable functions on X, real-valued measurable functions, where we identify two functions if they differ by a null set. So we can equip L0 with pointwise almost sure addition, multiplication, and ordering. In this case, L0 becomes an ordered, commutative, and unitil ring. So there are essentially two choices for convergence on L0. So the most used form of convergence is the topology of convergence in probability or convergence in measure, which is a metrizable, and interestingly, it is also a ring topology. So it makes addition and multiplication on L0 continuous. And we have also almost sure convergence, so pointwise almost sure convergence, but almost sure convergence is not, in general, not even topologizable. So now we consider the following random interval. So we take two measurable functions, f and g. So maybe I can just make a picture. So we have here two measurable functions, f and g. And then we look at all measurable functions which lie here in between. Okay? So this is, so since we have identified here on L0 functions which differ almost, so which are identical almost surely, this is not really a point object. Okay? So that's a point-free random interval. So in general, this interval is not compact in the topology of convergence in probability. But it is not difficult to see that it is closed under almost sure convergence. So if you have a sequence of function almost surely inside this, almost surely converging to some function, obviously that function will also lie in that interval. And it is also bounded with respect to almost sure ordering. What could happen is, of course, that, for example, the random variable g is unbounded itself, okay? But with respect to the almost sure ordering, this is still considered a bounded interval, okay? So we see here some form of random Heine-Borel theorem. So we have something which is closed and bounded. So we may wonder, is this object compact in a certain sense? So we can also consider a topology on L0, which is different from the previous one, which is the interval topology, where we declare the open intervals, Fg, to be the basic open sets. This is also a ring topology, but it is much finer than the topology of convergence of probability. So what is also important to notice is that the open interval or the closed interval is closed under a countable concatenation. So if you have a partition and we take on each partition a different element, okay, from this object, then we can concatenate these elements to a measurable object along a countable partition, and they will still lie in these open intervals or these closed intervals. Okay, now I want to introduce another notion of compactness in this context. So we say that the collection of subsets of this space of measurable functions covers a set X if for any element in that space X we find a partition along, so basically, so we find a partition and elements in those subsets which belong to C such that we can glue together those elements and those glued elements from those elements in the cover, they cover all of X. So it's not the classical union, but it is a union where we also allow all kind of gluings along partitions. So, and now we can define a notion of compactness. So we say that we have a cover of open intervals in this space of measurable functions, and we say that this cover, so we say that a set is compact if every such cover consisting of open intervals, there exists a partition such that on each partition element we have a finite subcover, and such that any element in that set X can be realized as a concatenation of those objects. So basically, what we do is that we cannot cover the whole thing by finitely many open intervals, but we can cover on each part. There is a partition such that we can cover on that partition with finitely elements when we are allowed to glue along those finitely elements of the cover locally on these partition elements. So with this notion of compactness, one can show that this interval indeed is compact. Okay. So now we can phrase a measurable version of the extreme value theorem. So we take a function from this closed or from this random compact interval into the space of measurable real-valued functions. We assume that it is continuous in the interval topology, and we assume that it respects concatenations, so meaning that this function also works well with, so my notation is not there. So this function, so if I glue together along partitions, then this commutes, this function commutes with gluings along partitions. So later that's just a sheaf morphism. So, but we'll come to that. So if you have, if you assume this, then we have another extreme value theorem here. So f is bounded in the almost sure ordering, and it attains a maximum and a minimum with respect to the almost sure order. So what goes into that? So the space L naught of all measurable functions, real-valued measurable functions, identified almost surely, is dedicant complete with respect to the almost order. This is at first for measure theorists a bit surprising, because usually only the countable supremum or the countable infimum of measurable functions are measurable. But since here we identify everything almost surely, also uncountably many suprema and uncountably many infima of measurable functions are measurable if we identify everything almost surely. So we are allowed to throw away a null set. So the second ingredient is indeed a Bolzano-Weierstrass type theorem. So if you have a bounded sequence of measurable functions, so bounded in the almost Scholl ordering, then there exists an increasing sequence of random indices, okay, and a limit such that if we parameterize that sequence with that random indices, this will converge almost surely. And if one uses these two ingredients, whose proof are not so difficult, one can prove this measurable version of the extreme value theorem. So this, this more direct approach. So what is the difference to the randomization or pointwise approach is that instead of formalizing everything pointwise and then applying classical theorems pointwise, we've actually formalized something in a point-free setting, and we applied measurable versions of results or proofs of, so we formulated theorems which can be seen as measurable versions of those classical theorems, which we then directly applied to the objects. And this approach, in some sense, generalizes the measurable selection theory, because one can show that there is a one-to-one relationship between compact values, F-ROS measurable set-valued functions, correspondences, and this new notion of compact subsets of L0, which are also closed under this gluing property. And one can also show that there is a one-to-one relationship between Karateodori integrands and continuous functions from L0 to itself in the interval topology, which respect this gluing property. However, the direct approach is much more flexible. So the direct approach can be generalized to allow values in any inseparable space. So, and the modified notion of compactness is also flexible. And we can actually also replace any closed valued measurable correspondence with any subset of L0 which is closed under countable concatenation. For example, open valued correspondences, which the measurable selection theory cannot cover, because one cannot guarantee the existence of measurable selectors in these cases. And measurability in this direct approach is actually automatic. So we did not at any point needed to apply a measurable selection theorem. We just measurably changed the proof, and so the outcome of this proof is automatically measurable. And we didn't need any countability or separability assumptions. However, there are some measure-theoretic countability. So separability is a topological countability assumptions. But now we replace those topological countability assumptions with measure-theoretic ones. And the measure-theoretic ones is that we need the underlying, so we worked with a probability space, but we can do a little bit more generally. We need that the underlying measure space is sigma finite. This guarantees that we can work with countable partitions here. And the gluing with countable partitions preserves measurability. And we need to identify all the objects and relations almost surely with respect to that given measure. And we have to request that all objects and relations have to satisfy this countable concatenation property. So let's do this. So actually there is a topos which corresponds exactly to this reasoning. And the measurable Bolzano-Weierstrass theorem and its proof, which I sketched out, is actually an example of the internal discourse of that topos. So what is this topos? So we start by identifying on the basic level of the probability. So we have given a probability space. So usually this is a sigma algebra, right? So it is only closed under countable unions and intersections. But what we can do is that we can quotient out the ideal of null sets. So these are all sets which are given the measure 0. So that's a sigma ideal of the sigma algebra. And if you quotient this out, then the quotient algebra satisfies two key properties. So one property is a countable chain condition, meaning that partitions in this algebra are at most countable. And the second condition is that this algebra now is complete. So it's a complete Boolean algebra. So we can form arbitrary joins and meets. So on that complete Boolean algebra, we can define a Grothendieck basis. So this is a function taking any element of this complete Boolean algebra and associating to it the set of all partitions of that element. As I mentioned before, so these partitions are at most countable. So, and this Grothendieck basis is a basis for the subtopology on the complete Boolean algebra. And so we can construct a Grothendieck topos of sheaves on that side. Okay? So this Grothendieck topos has a very rich internal logic. So it has a natural numbers object, it is Boolean, and it satisfies the axiom of choice. So in fact, one can show something very remarkable, at least for me, that the objects of this topos form a Boolean valued model of set theory. So this means that any theorem which we know in set theory has actually a realization in this topos, which is true with probability 1. So let's see what are the real numbers in this topos. In fact, one can show that the real numbers are actually the space L0 up to isomorphy can be identified with the space L0 of real valued measurable functions identified almost surely. So what is a corresponding sheaf? Well, for any A in that complete Boolean algebra, we can define L0A to be all measurable functions restricted to A. And then we can define the restriction operations to just send a function which is, so if we have here a measurable function, we can restrict it to B, and then the restriction on some subset A is just giving this map. And with this restriction maps, one can show that indeed this is a sheaf in this topos. And this sheaf is a realization or is an interpretation of the real numbers in this topos. The measurable version of the Bolzano-Weierstrass theorem, which I showed before, is actually an external interpretation of the Bolzano-Weierstrass theorem inside this topos. Now, the power set of the real numbers, because I want to just give you some intuition, or at least my intuition, for how certain objects look like in this topos. So the power set of the real numbers can be described as pairs x and a, where a is just the element, the local element on which the set lives, and x is a subset of L0, which is just closed under this countable gluings. So now let's see how the set union looks like internally. So we have here two sets, x, which lives on A, and we have here another set y, which lives on B. And if we take their union, then we have to consider measurable functions which can be, which are partially here and partially here. So we have to take the usual union of those, but also all the possible gluings. How about the intersection? So if you have here again another set x, which lives also locally here, and which actually lives here plus here, and then we have a set y which looks like this. Then the intersection of this is those pink areas here. Okay, so the intersection, for example, lives on some measurable set which is much smaller than the measurable set on which the other two sets live. How about the complement? So what can happen in the case of the complement is that we can have sets which are locally empty in that sheaf, and we can, and which are locally everything. And if you want to take the complement, then where it is locally empty, we have to be everything. Where it is locally everything, we have to be nothing. And where it is something, we have to just complement it. But for example, this element is not in the complement. Because here, locally, on a positive probability, it falls within this green element. Okay, so what are some other examples of such measure-theoretic sheaves? For example, we can just modify the definition for the real numbers. We can just take any measurable space and look at all measurable functions from X into that measurable space, identified almost surely, and this gives us a sheaves inside this topos. We could, for example, start with a Banach space, E, and then instead of considering all Borel measurable functions, we consider only strongly measurable functions. So strongly measurable functions are functions which can be approximated by simple functions. So if we are in inseparable settings, and these two notions of Borel measurable and strongly measurable do not necessarily coincide. This strongly measurable assumption guarantees that the norm, this norm is a measurable function, and then this turns this sheaf here into an internal Banach space. So we can also define sheaves more abstract sheaves, which are completely point-free. So instead of considering here a measure space with an underlying set, we can also just consider any sigma-complete Boolean algebra and look at the collection of all Boolean sigma homomorphisms from that Boolean algebra into A. And here is another construction which is not of this form here. So suppose the probability we start, so we have a probability space, started with a probability space xf mu, and suppose we take a sub-sigma algebra of f, okay? Then we have a conditional expectation operator. That's so basically, if you don't know what it is, so we have to x associated a Hilbert space L2, and then we can look at the Hilbert space of G measurable functions. And then the conditional expectation operator is an orthogonal projection. Okay? So that's a very useful notion in probability and also ergodic theory. And so this is what is denoted here. And we can now define what we call the conditional L2 space. So we take all functions which are measurable with respect to the larger sigma algebra and look at this such that their square has finite conditional expectation, almost surely. So the conditional expectation is itself some measurable object. Then one can show that this object here can be interpreted or is internally a Hilbert space, and with the following inner product, okay, where the inner product between those measurable functions is just given as a usual Hilbert space product, but you replace expectations with conditional expectations. So now let me give you two applications into ergodic structure theory. So let's fix an arbitrary discrete group gamma, and we consider a probability algebra, so a probability or a probability space, just imagine a probability space. And let's look at the automorphism group of this probability space. So these are all measure-preserving, bimeasurable bijections. Okay, and then we can define a measure-preserving dynamical system as a tuple consisting of a probability algebra and a group homomorphism from the external group into the automorphism group of the space. So a factor of a measure-preserving system is another measure-preserving system where there exist Boolean homomorphisms between the underlying measure spaces, probability spaces, and measure-preserving, which intertwines the action. So now, given a measure-preserving dynamical system, we have a basic representation of its Koopman operator. So the Koopman operator is just a lift of the action on the space on the corresponding L2 space. And this gives a unitary representation of the external group gamma on L2, and this unitary representation splits in L2 into the finite dimensional parts and into the parts which do not admit any finite dimensional representation. So this part is usually referred to as a compact part as a system, and this part is referred to as a weakly mixing or random part of the system. So this is a very classical decomposition result in its initial form, going all the way back to von Neumann and Halmos. However, this primary decomposition does not capture all the structure in a system. So here is an example. So consider a skew product extension. So we have a Z system where we have a torus by torus extension. So we have a torus on which we have just a rotation by some, for example, irrational number. So this gives an ergodic action. And then we extend this torus by another torus where the dynamics on the second component are given depends on the first component. Okay, so it's kind of, you can imagine it as a fiber above the first torus. So this looks like a pretty structured or compact system. The compact part of this system is just this the first coordinate. So it is the base system with a rotation on it. However, relative to that part, the second part is also compact. Okay, although in this decomposition cannot see this. And this is what in ergodic theory is called a compact extension. So now, how can we analyze those compact extensions? So there is, so this is important in certain areas of ergodic theory, which, for example, are related to what is known as Fürstenberg-Zimmer structure theory, and their applications, for example, in combinatorics, in the form of Samaredis theorem or in number theoretic applications. So understanding these compact extensions. So these compact extensions, or the representation theory of, or theory of these compact extensions, to study them, one has to formalize an analysis which is done relative to a factor. So classically, this has been done using measurable Hilbert space bundles or direct integrals. And for this, one needs to disintegrate the measure. So we had a factor map from the underlying measure spaces. This gives a disintegration. And then this allows to fiber-wise analyze this topic with some bundle theory. So this is very similar to the approach which I try to explain in this motivating example at the beginning with the extreme value theorem, where we had also a pointwise approach. But it also lacks the same restrictions. So measure disintegrations only exist under certain separability or countability, so countability assumptions on the acting group, and separability assumptions on the underlying probability space. So alternatively, one can also translate this problem into the topos of Measure-Theoretic sheaves on the factor algebra. So relative to that, so for example, relative to that base circle. And then in this context, representation theory of these compact extensions is just the internal, or one can analyze this with the internal Hilbert space theory of this conditional L2 space, which I introduced before, which is a Hilbert space, internal Hilbert space. And basically, given that we have a logical transfer principle, this representation theory of compact extensions just directly follows from the internal logic of this topos from basically this classical decomposition. So here is another example from measurable cohomology. So suppose gamma is now abelian, and we have a measure-preserving system with respect to abelian action, and K is a compact abelian group. So a cocycle, a measurable cocycle, is a map from gamma times X to K. So X is underlying space, such that for any gamma 1, gamma 2, we have the following cocycle identity. Okay? So in this context, we call a cocycle a coboundary if there exists a measurable function f from X to K, such that for each gamma, this cocycle is a coboundary where, yeah. So we replace actually here the group law or action by the external action of the group gamma. So one can show in the measure-theoretic or in the ergodic context that if a cocycle is a coboundary, then it doesn't add any additional dynamics to the system. So a coboundary extends the original system. So it's, if you extend by a coboundary, then you obtain a system which is isomorphic to your original system. So it is important to classify those cocycles which are coboundaries. And then there is a classical theorem of Moore and Schmidt which provides a way to test cocycles when they are a coboundary. So a cocycle is a coboundary if and only if we test it with all the characters of this compact abelian group. So then this cocycle becomes torus valued. These tested cocycles are all coboundary. The proof of this result has certain restrictions. So if one wants to prove this result, there is a pointwise formalization of this theorem. So this leads to certain restrictions. So gamma, so the acting group, for example, has to be taken to be countable. That compact abelian group with respect to which one extends needs to be metrizable, and the underlying space has to be separable. However, one can also follow a point-free formalization, and we did this in a paper with Tao, where we proved a very general version of this Moore-Schmidt theorem, where we dropped all the assumptions, like gamma can be anything, X can be anything, K can be anything. Even we can have here sigma finite measure, not probability measure. We can have a non-ergodic system. And basically the tool which, we didn't write it in this way, but basically the tool which runs it is the internal Pontryagin duality of the topos, so the internal Pontryagin duality between compact and discrete abelian groups in the topos over the measure algebra of X. If one just accepts this as granted, so we proved it by hand, the externalization of this statement we proved by hand. But if one believes in the transfer principle and accepts this as a fact, then the Moore-Schmidt theorem is just a simple corollary in its most general form from this internal result. So finally, I want to give another application to vector duality. This is a bit still work in progress. So let E be a Banach space, and let's consider the Bochner space of P integrable, strongly measurable functions. A classical question from the 70s is that what is a dual space here? So we know what is a dual of an LP space. It's an LQ space if you have real valued functions. But if you have Banach valued functions, it's not clear what this dual space is. And then there is a condition which is known as a Radon-Nikodym property. So the Radon-Nikodym property is a property of vector measures. So one can consider measures with values in the dual of this Banach space E. And one says that this vector measures has a Radon-Nikodym property if there exists a Bochner integrable function with vector valued function, such that this measure can be written as in the sense of this Bochner integral. And then there is this beautiful theorem which says that if the dual space of this Banach space satisfies the Radon-Nikodym property with respect to the underlying measure space here, then for all P, I think here you can take also P equal to 1, we have this duality. So LP of X, E, the dual space of this guy is the same as LQ. So that's what we know from basic real analysis. So one can interpret this fact topos theoretically. So this, so one can show that, so I gave this as an example before, so if one, instead of LP, one looks at L0 in the space of all measurable functions from X into that Banach space, then this is an internal Banach space. And one can wonder what is a dual space, the internal dual space of this Banach space. And one can show that if E star satisfies a Radon-Nikodym property, so a classical property, then this has a consequence of also in the internal logic of this topos, because a dual of this space can be identified as L0 with values in the dual, in the classical dual of this Banach space. So this interpretation, it's maybe a cute observation, but it actually suggests a way to analyze this question here, what is a dual space, beyond the setting of the Radon-Nikodym property. So we had, if the dual space of the Banach space satisfies the Radon-Nikodym property, then we had this nice interpretation of the dual space. But if not, we don't know what this dual space is. And, but by lifting this problem into the topos, this gives us additional tools which allows us to study this dual space and try to make sense of what the dual elements could look like here if E star does not satisfy the Radon-Nikodym property. And that's all what I have.